So we now know what ODE is. Then you often hear the term the solution of the ODE or the differential equation. The solution means go ahead and find the y that satisfy the differential equation. So for example, dy dx equals to sine x. So what y will satisfy this? So y is equals to minus cos x will satisfy this, but actually y equals to minus cos x plus k, any k will also satisfy this. So this is the general solution of the differential equations for this guy. Now, sometimes you'll be told the required interval where the x-axis. Okay, so when you have found your solution, the way to check whether you have found the solution is like what you have done or I have done is that I take this expression, perform the derivative, and then I check whether it agrees with the differential equations along with all the initial value conditions sometimes are given to me. So for example, if I say this is plus 3, then I should say when x is equals to some value, then y is equals to plus 3, for example. Okay. Now, if you have done ordinary differential equations in other courses, for example, Math 1, then you'll realize that there are many methods to solve ordinary differential equations. In this course, we are only reviewing ODE, and we'll show you how to use Laplace transform to solve ODE. And if you remember that it was really difficult to solve ODE, I mean, there are many methods, and you have to remember many of them. And when it comes to using Laplace, it's a much simpler process. So if you want a quick review, just go to YouTube, Google Lazy Engineer review of first order differential equations, and then you'll see this slide. Alright, let's talk about other terminology that is of use to us. So we talk about solution, and then there's a word called general solution versus later on something called a particular solution. Alright, let's see what a general and particular solution is. We are given some constant coefficients ODE. Here the word constant means the expression in front of these differentiation expressions are all constant. In this case is 1, here's 1, here's 6. Ordinary because it's only dy dx. And here's the second order because we only dealing with d2y dx squared. And on the right hand side, when the expression on the left equals to 0 on the right hand side, this is called homogeneous. So this is a homogeneous ordinary differential equation because the derivative of the dependent variable is equals to 0 on the right hand side. Alright. Now, in this example, he says that the solution is some exponential of RT where R is unknown, and then he says I found R1 and R2 to be this value, and then this value can then be put into this is R1 and this is R2. However, we still have all these constants to find, so these are the little tricks that this kind of tutorial will teach you how to find solutions like this. Right. Once you have found these coefficients, and then, but how do we solve C1 and C2? He has to give you additional information, like what is y when x is equals to 0, or in this case not x, sorry, the independent variable is t. So y when t equals to 0 is equals to 1, y prime, so dy dt at time equals to 0, t t equals to 0, the expression is equals to 2. I shouldn't write like this. Maybe I change this into like this. T equals to 0. So when we have this given initial values, we can go and solve for C1 and C2. Alright. So we call this a particular solution. And this is the general solution. The word particular here, you can think of it as to satisfy a given initial condition. Now, then you'll see that we do it even one step further. The right hand side, we solve it actually for 0 first. So we call this the homogeneous solution. But now we change the right hand side to have some expression that is non-zero. In this case, we want to solve for these differential equations given this extra condition, even additional to the initial value. So this is typically the driving function, and we call this solution the particular solution as well. So this expression is found with this information, where this blue is found when we have a homogeneous solution. Okay, so there are a few terminologies going on. You have to remember them. I have provided links where you can listen to this gentleman here to talk about how to solve constant coefficient homogeneous differential equation on the first example, and solving non-homogeneous ordinary differential equation in the second example. Okay, this is my last example for ordinary differential equations. We're saying that find the solution that exists for this interval, the entire interval on the real line where x goes from negative infinity to positive infinity. And we're told that dy dx is equals to this guy. Also, this is actually a non-linear differential equations because we have these terms here. But never mind, we are just asking ourselves to prove, because we are already given the solution. Y is equals to x4, x to the power 4 divided by 16. So on the left hand side, let's work it out. On the left hand side, we have dy dx equals to, and we plug in the value of y into here. The value of y is x to the power of 4 divided by 16. So we are interested in 4 over 16 x3. Okay, so we get this expression here, 1 over 4 x3. So this equation is 1 over 4 x3. What about the other side? So we plug in y into here, so it's x, and then we have square root of x4 over 16. So this expression is this. We can take the square root, which is x. So x4 becomes x2, 16 becomes 4. And then we multiply. And then we see that, okay, left hand side equals to right hand side. Therefore, the solution is correct. So this is just like if I've given you the solution, then you just plug in the dependent variable into this differential equation expression and work it all out, and then if it equals, then the solution is correct. That's the idea. Okay, thank you.